In today's lesson, we're going to be learning about the first of our integration techniques, integration by substitution. These problems can get really complicated, but for today I'm going to try and keep it pretty simple and just get you a sense for how the technique works. Before we get into that, let's go and take a deep breath. And let's begin. So, integration by substitution is undoubtedly the most commonly used of all of these integration techniques. And what it really does is it effectively undoes a chain rule derivative. And I want to try and sort of illustrate some of the motivation for integration by substitution. And so we're going to look at a really quick example that's actually kind of not about integration at all. It's actually about derivatives, right? So suppose that I gave you this function, y equals 6 times the sine of x cubed. And then I asked you to find dy dx. Now remember that this notation dy dx means the derivative of y with respect to x. So dy dx is just a notation that we use to say the derivative of y with respect to the variable x. So pause the video and just do a quick chain rule derivative to find dy dx. So you should have found here that dy dx, like our inner function here is x cubed, and our outer function is like 6 sine x. So the derivative of this should be 6 cosine of x cubed times the derivative of what was inside, so times 3x squared. So that means that dy dx is 18x squared cosine of x cubed. Okay? So what we just did there is we sort of wrote down that the derivative of 6 sine x cubed is 18x squared cosine cubed. Now the second thing I asked you in this example is I want you to write an integral expression that expresses this. So can you express this same understanding, this same meaning as an integral? If you think you've got an idea of how to do that, please pause the video and write it down now. You shouldn't need to do a lot of math for this. It should just be a notation, a thing that you're writing. What you should have written down is if this is the derivative of this, it means that the antiderivative of 18x squared cosine x cubed, the antiderivative of that should be 6 sine x cubed plus c. And all I really wanted to illustrate through this example was that when we take a derivative of something, we automatically can write that as an integral expression. But now that we know that this integral is this, we might be curious about how we could have found that if we hadn't started with that knowledge. In fact, if you've been paying attention as we've been sort of reviewing integration, I've made a lot of noise about the fact that we don't know how to do this integral. Like it's got something stuck inside of the cosine, it's two functions multiplied together. This feels like a perfect example of the kind of thing that just a couple of days ago I would have said, oh, we don't know how to do this. And so that's what this lesson's going to be about. It's going to sort of be about how do we do integration by substitution. So in the next slide, I'm going to show you what exactly the steps are. For this one, I'm just going to show you the process so you have a sense of what those steps are going to be when we talk about them. So in this problem, I'm wanting to find out what the antiderivative of 18x squared cosine x cubed dx is. And my thinking here is that I really wish that this thing inside wasn't complicated. I wish that was just a single variable. And so I'm going to start this process by making a substitution. I'm going to say let u, the thing I'm going to substitute for, let u be x cubed. Okay. The next step is that I take the derivative, du dx. The derivative of my substitution is 3x squared. That's just me using the power rule to do a derivative. The next step in the substitution process is that I'm going to multiply this dx over. I basically want to solve for dx. So du is 3x squared dx. And then similarly, I'm going to move this 3x squared over. So du over 3x squared equals dx. Okay? And what I have at this point is I basically have a substitution that will let me replace x cubed and a substitution that will let me replace the dx. So my next step in this integration by substitution is to use my original substitution where it is inside the problem, and then to use this dx substitution on the dx at the end of the integral. So I'm going to do that now. So this is going to be the integral of 18x squared cosine of, and I'm replacing the x cubed with u, and I'm replacing the dx with du over 3x squared. And my goal in u substitution is to somehow get the integral to change from being entirely in terms of x to being entirely in terms of u. And I'm close here, but you'll notice there's still some x's lingering. But the good news is, though, that there's an x squared on the bottom here and one on the top. There's even a 3 here in the 18, which will reduce down to 6. So at the end of all of this simplifying, I have the integral of 6 cosine u du, and I want you to notice that at this point in the problem, I've transformed this from being a really complicated integral into one of those really, really simple things that we know how to do. All I need to do now is use the constant multiple rule to bring that out. And then I know the integral of cosine u is sine u, so this would be 6 sine u plus c. And then the final step in the whole process is for me to go, hey, wait a minute. This problem was really about x originally, so let's take that u substitution that we used and plug it right back in at the end. 6 sine x cubed plus c. You'll notice that that's exactly what we found that it was supposed to be based on the previous work that we had done. So this has been an example of integration by substitution. Next, we're going to sort of go into what are the steps that we take to do this? How do we learn to do this consistently on our own? So the steps in this process. Step 1, we select a substitution if one isn't already given and label it u. So sometimes the problem will give you the substitution. If it's particularly complicated, they'll give it to you. If not, then you choose it and you label it u. The second thing we do, you remember from the previous problem, we take the derivative and we write that as du dx, and then we solve for dx so that it's in terms of du. The third step is that we replace the dx with what we found, and we look for any obvious occurrences of u and replace them with the thing that we set up in part 1. Step 4, you simplify as far as you possibly can, with your goal being taking that integral in terms of u. I suppose I should say in step 4, what's really supposed to happen in step 4 is that all original variables should vanish, which doesn't mean you just erase them. It means that you get them all to cancel or to substitute out. And then remember, at the very end, after you've integrated it in terms of u, you want to go back and rewrite it in terms of x by reusing that substitution. Now, I do want to be honest with you. There are some additional steps sometimes, but I'm going to save those for later. For today, I really just want to get through basic applications of integration by substitution, and we'll get to those potentially tomorrow, maybe a little bit further down the line. So in this first example, I've really written out what all the steps are, and I've sort of shown you in the places that I usually like to structure them in a problem, just so that you guys can have a framework for how you should try and organize your work. Integration by substitution is a process that really requires that we be precise and careful. Canceling one thing wrong can throw the whole thing off, which doesn't mean that it's super hard, it just means that we need to be careful. So step 1, I usually, because I'm going to do this first, I write it out in the upper left, right? They told me that u is going to be 5x minus 4. Okay? Right underneath that, I keep working out this substitution, right? So I'm using some of my vertical space here to find du dx. So du dx, the derivative of that is just 5. Okay? And then I'm supposed to solve for dx. So I'm moving that dx over, and then I'm dividing the 5. So I get that du over 5 is dx. Okay? Now in step 3, I'm kind of going back up to the top of the problem. So this is where I did work on my substitution. I'm now going to take this information and restart the problem up high so that I can work through the space down on the right of my paper. Okay, so I'm going to rewrite my integral, and I'm going to replace the dx, and I'm going to replace the obvious occurrences of u. So my original integral, which was the integral of the square root of 5x minus 4 dx, is now going to be the integral of the square root of u times du over 5. Okay? In step 4, I'm just continuing this work, okay? At this point, I want to simplify as far as possible, and I want to work out this integral. So my next thought is, constant multiple rule should let me pull out that 1/5, and I'd really like to rewrite that u as a 1/2 power, because I want to use the power rule, Right, so now I've got it nice, clean, simple. It's going to be easy for me to take this antiderivative. From here, I'm just supposed to increase the power by 1. So I'm supposed to add 1 to this power and then multiply by the reciprocal of that thing. So that power is going to become 3/2, and I'm going to multiply by 2/3, and the constant multiple is still waiting out there, and I've got my plus c. Okay, I suppose I could, I'm running out of some vertical space here, I suppose I could even put those together to make this 2/15 u to the 3/2 plus c. And then step 5, my final step on this thing is to say, hey, I finished this thing. I took the antiderivative. Now I just need to put it in terms of x. So I'm now going to write this integral, this answer, 2/15, but instead of u, I'm going to write 5x minus 4, which was my original substitution, that raised to the 3/2 power plus c. This is what the process of u substitution looks like. And again, I really, really, really need you guys to be precise on this, that you write the integral symbol every time until you've taken the integral. So if you haven't taken the integral yet, please write that integral symbol. I want you to write the dx, write the du, write everything that should be there. In some of your work, some of you will sometimes leave things out or do a little side note on the side. In these problems, it really, really, really pays to be precise and write all of this stuff out. In all of the rest of my examples, I'm not going to have these reminders about what the steps are. So if there's any ambiguity for you or any concern, pause the video here, look through it, make sure you understand what's happening here, because we're really going to apply this exact same process to all the rest of the examples that we'll go through today. So in my next example, simplify the integral 5 cosine x sine squared x by letting u equal sine x. So once again, for this example and the next one, I'm going to give you the substitution. U is sine x. For this one, I'd really recommend that you guys sort of pause and unpause the video to follow my steps as we go through this. So why don't you pause the video and go through step 2 right now. Step 2, you should have done du dx is the derivative of sine, which is cosine x. The other thing that happens in step 2 is that we solve for dx. So we multiply the dx over cosine x dx, and then I divide by the cosine. Du over cosine x equals dx. So we've done step 1, we've done step 2. Step 3 is we go back to the original integral, the integral 5 cosine x sine squared x dx, and I use my u substitution and my dx substitution. Okay. Now, you might need to take a step here to simplify this first. You might need to take a moment to remind yourself, what does sine squared x mean? Doesn't that mean sine x squared? And if you haven't already done this, I want you to pause the video and go through this substitution and see if you can make all the x's in the problem go away. So you should have had here 5 cosine x times u squared times du over cosine x. And as you were doing this, you might have sort of worried, oh no, what am I going to do with the cosine x? But as soon as you write this, you realize, hey, good news, these cosine x's are going to cancel one another out, and what I'm left with is just the integral of 5u squared du. Right? So I've transformed my integral from being in terms of x and being complicated to being in terms of u and being simple. Constant multiple rule, we pull out the 5. And then this integral is really simple. It's just 1/3 u cubed plus c. And so the final thing I do is I put my u back in. This is 5/3 sine cubed x plus c. Okay. If you don't see where that came from, by the way, this was just 5/3 times sine x cubed plus c. But then I decided to write it this way, like sine cubed, because it's just sort of a cleaner notation than that one is. So I hope that this one made sense. In the next example, I'm going to encourage you to really just go through it all on your own and see if you can get through it. All right, so go ahead and try doing those 5 steps and see if you can get through this one. So step 1, we write down our u substitution. Whoops, I said u at the wrong time. 6 minus 3x squared. And then du dx is negative 6x. That means du is negative 6x dx. That means du over negative 6x is dx. So now I have my u substitution completed. I have my dx substitution completed. And so now I actually begin doing the integral. I have the integral of 4x over Now that whole bottom is u, like it's right there. So this is 4x over u times, and then I replace my dx with du over negative 6x. And again, if you were worried about this x being here, great news, it cancels out. Some of you may be wondering, does that always happen? The answer is kind of. Either that means that your u substitution didn't work, or you're dealing with a more complicated problem. For what we're doing today, you're going to find that those x's are always going to cancel out. It's always going to be really nice. So as I continue to simplify this, actually the 4 and the 6 will also simplify. I've got negative 2/3 times 1 over u du. Constant multiple rule lets me pull out the negative 2/3. And then I remember that my integral of 1 over u is the natural log of the absolute value of u plus c. And then the very final step is that I'm supposed to put this back in terms of x. So this is negative 2/3, the natural log of the absolute value of 6 minus 3x squared plus c. I can't emphasize enough how much these are the 5 steps of u substitution, of integration by substitution. So if you can get this down, and if we can get really solid at this today, we can start to talk about some of the more complicated applications. In all of the previous examples that we've done, I've done some of the hard work for you. I've always given you that u substitution. And so at this point, we're moving into the final phase of this lesson. And that phase is, how do we choose our own substitution when it isn't given? And I want to be really honest with you. Choosing the appropriate substitution is challenging. It's something that requires practice, it requires intuition. Honestly, it requires doing these problems wrong, getting the substitutions wrong a couple of times, and seeing what's causing that to happen. So I really, really would encourage you guys to be reflective as you're working through these problems. I'm going to try in the assignment that I do for this one to make it a little bit shorter so that you've got time to really think about what you're doing instead of trying to just race through all of the problems. And there really isn't any hard or fast rule as to how to choose your substitution, but I can give you some guidelines. Okay, and there's really sort of 3 main guidelines. The first guideline is that your substitution should be composed into another function. In other words, your substitution should be inside of a cosine, or inside of a sine, or it should be the exponent of an e to the x function, or it should be the denominator of a 1 over something function, or it should be plugged into a squared function or into a fifth function. Like, integration by substitution is about undoing the chain rule. So very often your substitution is going to be something that looks like it's the inside part of a chain rule. Okay? The second guideline here is that the derivative of that substitution, or at least the variable part of it, should show up somewhere else in the integrand. So if you are planning on using u equals x cubed as your substitution, the derivative of that is 3x squared. You should be seeing an x squared somewhere. Not always, but usually. And then the third recommendation that I have for you down here, the third guideline, is you'll almost always choose the whole expression and not just a part of one. So if your integrand has something like the sine of 3x squared minus 4, I can't think of any case where you would actually use just, okay, never mind, I did just think of one of them. It's very rare, though, that you're going to use just part of a term. Particularly for this intro lesson, it's really the whole term that you're likely to want to use. So before we get into our last few examples, I want to sort of give you guys a little bit of practice with trying to choose what your u would be. And so what I've done is I've taken the 3 examples that we're going to do in the rest of the assignment, and I want to give you an opportunity to sort of look at each of them and not try and do the whole problem at once, but just think about what would you use as a substitution. So I want you to pause the video and think about these guidelines that I just gave, and for each one of these things, choose the u that you think you'd want to use, and think, or maybe even write, what's your reasoning for that? Why are you wanting to choose that thing? Right. So now let's go through them one at a time. In this first one, I think it makes the most sense to use our u as 5x squared minus 3. Now what's our reasoning? Our reasoning is 5x squared minus 3 is composed inside of a power. That's good. The derivative of 5x squared minus 3 is 10x. And 10x, it's not quite x, but it's a multiple of that. So it seems close. This is going to be the substitution that's going to work for this problem. Okay, so we'll do that problem in just a minute. Let's go on to the second one. If you haven't thought about this u substitution yet, I'd encourage you to think about it now. This next one's a little bit harder, right? Then this next one, the thing that makes sense for us to use is 3x squared minus 6. And you might sort of wonder why. Well, one of the reasons is that it's the denominator of a function. It's the denominator of something like 1 over x, right? In addition to that, the derivative of this is 6x minus 6. And I don't see a 6x minus 6 in the problem, but if I factored 6 out of that, it would be 6 times x minus 1, which is exactly what's in the top. So this one is a little bit hard to see, but this would be the appropriate choice of u for this one. Okay? And then finally, let's go on and take a look at this last one. If you haven't thought about it, think about it for yourself. For this one, the u choice, it makes sense to do the natural log of x. And again, we think about why. First of all, that natural log is composed inside of a sign. That's good news. On top of that, the derivative of natural log is 1 over x, and this problem actually has an over x in it, right? And so it's meeting all of these requirements of things that we're trying to do in order to get our u substitutions to work. So now that we've talked about what these u substitutions are going to be, our next 3 examples are literally going to be going through these problems using the u substitutions that you just chose. So this is the first of those 3 examples that we just talked about setting up. So you already know that the proper u to use is 5x squared minus 3. That's step 1. I now want you to pause the video, go and try, steps 2, 3, 4, and 5, and see if you can get through this process. So the derivative du dx is 10x. That means that du is 10x dx, and that means that du over 10x is dx. I've got my u substitution, I've got my dx substitution. I now bring them to the original problem, the original integral, and I substitute them in and hope to see good things happen. This is going to be the integral of x times u to the 4th, and then my dx gets replaced by du over 10x. At this point, we're starting to not be surprised anymore when we see that these things cancel out. Remember, when you've done your u substitution properly, for a simple one of these, those x's are always going to cancel out and go away. Okay. Continuing on in the process, I now have the integral of 1/10 u to the 4th du. Constant multiple rule lets me bring out the 1/10. My integral of u to the 4th is 1/5 u to the 5th plus c. And then the final step is just for me to put this u back in and write out my final answer. 1/50th 5x squared minus 3 to the 5th plus c. There we go, u substitution. By the way, you might have noticed that sometimes I call this u substitution, sometimes I call it integration by substitution. It really names for the same thing. It's often called u substitution because u is the customary variable that we used when we substitute. But I think I like calling it integration by substitution because it really lends itself to the idea that substitution is a technique of integration, and we're going to learn lots more of them. All right, so let's go on to the second one now. You may have forgotten what u substitution we chose earlier. If you did, I'd encourage you to look at the problem through a fresh set of eyes and see if you can remember. See if you can see what makes sense here to use as our u substitution. I'm going to choose my u to be the denominator, 3x squared minus 6x. That means that du dx is 6x minus 6. I do need to take a little care here. When I multiply the dx over, remember to put this in parentheses, 6x minus 6 dx. And then I'll divide this over. Du over 6x minus 6 equals dx. Just like we've done before, I now have a complete u substitution and a complete dx substitution. So I'm going to bring those back to the original integral. It was originally x minus 1 over 3x squared minus 6x dx. My x minus 1 I'm not sure what to do with yet, but the bottom is very clearly my u, and my dx is a simple substitution. This is just du over 6x minus 6. Now we might be worried here because these things are not canceling out magically like they always have before, right? When that happens, it doesn't mean you did it wrong, it just means you may need to do a little bit more work. In this case, we can notice that the denominator factors into 6 times x minus 1. And once we have that, we can see that these do cancel out. And that was exactly the x term that we needed to cancel out. And so now I can rewrite this as the constant 1/6 1 over u and du. Constant multiple rule lets me bring that out. And so I have 1/6 the natural log of the absolute value of u plus c. And then my very final step is to take my original u substitution and plug it back in. So this will be 1/6 the natural log of 3x squared minus 6x plus c. I've noticed that on the last two problems, these have really only taken us about 2 minutes to do. So I want to point out to you that integration by substitution is a technique. It can be complicated, but when done properly, it only takes you a couple minutes. That also means that even when you do them wrong, it doesn't take you a long time to get it wrong, and then to think about what went wrong and try and adjust your method to make it work right. So I hope that you guys won't use, I hope that mistakes that you make on these problems won't keep you from pushing forward and figuring out how to do this. You can get this. You're going to get good at this, and we're going to be excited to move on to other integration techniques down the line. So let's look at our one final example. Okay. In this last one, hopefully you recall that the u that we're going to use is the natural log of x, and the reason we're doing that is that it's plugged into sine. It's composed inside of something. I know this is our last example, so this is your last chance to do a problem on your own. So pause the video, do the rest of this one on your own. Du dx is 1 over x. So that means du is 1 over x dx, which means that x du is dx. And this might seem a little strange because we almost always have a fraction that's left here, but sometimes we won't, and that's okay. Let's see what happens when we take these substitutions that we have and use them to rewrite our integral. My integral was supposed to be the sine of the natural log of x over 3x dx. And now, plugging these things in, I'm going to get the sine of u over 3x times x du. And at this moment right here, we're thankful that this thing wasn't a fraction because I needed that x to be on top to cancel with that one. As we've seen with all of these problems, all of my x's drop out, and I'm left with this really simple integral that's just in terms of u. Okay, constant multiple rule, I bring out the 1/3. We then remember that the antiderivative of sine u is negative cosine u plus c. And then my final step is just to bring this substitution back in and beautify my final answer. I'll make it negative 1/3 cosine of natural log of x plus c. This is integration by substitution. As I alluded to partway through the lesson, there are some complications that can come up, and we'll get to those. But for now, this is sort of the bare bones basic version of integration by substitution. As always, if you have questions, if you're confused about some of these things, rewatch those parts of the video or send me those questions, and I'd be more than happy to help you. So best of luck as you work through these exercises. You got this.